Hi, everybody. This is a lesson on non-conservative forces. This lesson addresses targets 11 and 12, which have to do with converting mechanical energy into other forms of energy and looking at the effects of friction when friction does work on objects. You can find the notes for this presentation on our classroom webpage, and you can download those if you would like, or you can write them down in your own physics notes. So first of all, let's review. We talked about gravity as being a conservative force. And we said that that's true because gravity has its own form of potential energy, known as gravitational potential energy. The work that gravity does will cause a very specific change in that potential energy. And that's given by this expression right here. The work by a conservative force is equal to a negative change of the potential energy. We talked about how when gravity does work, if the object returns to its original height, that gravity does a total amount of work equal to zero. So the round trip work is zero. And we know that the work done by gravity is reversible. That is, you can do positive work, you can do negative work, depending on if an object is going down or up. And lastly, we talked about the idea that work is independent of path, that it doesn't matter how you change the height in a situation, all that matters is the actual height difference. Okay, so the counterexample here would be the force of friction, and friction is a non-conservative force. And the first thing to kind of clue us into that is that friction does not have its own form of potential energy. There's no frictional potential energy. In fact, the work that friction does is converted into thermal energy. And thermal energy is considered to be non-mechanical because it is not associated directly with the potential energy or the kinetic energy of a large macroscopic object. So the work that's done by friction causes a change in another form of energy, which is thermal energy. And that work that's done by friction is related to the change in the non-mechanical energy in a very similar way to how the work by a conservative force is related to a change in potential energy. So that's this here. So NME stands for non-mechanical energy. So think about friction. We know that friction can only do negative work. It can never do positive work. So there's no way for the work by friction to cancel itself out. Okay, so that can't happen the same way that it can happen with a force like gravity, and the work is definitely not reversible. Okay. Lastly, the work done by friction is path dependent. The longer the path, the more work friction is going to do, which is somewhat different from the gravitational force, in which the work only depends on a height change. Okay. Also review. When we talked about conservative forces, we showed that the mechanical energy has to be conserved. And we started with the work-kinetic energy relationship, and we did some substitutions to kind of show us that the total amount of kinetic and potential energies have to always add up to the same amount, both before and after. Okay, and so that's an extremely useful feature of physics, that if you have only conservative forces, say like gravity, that the mechanical energy will always be conserved. Now, it gets a little bit messier when you have non-conservative forces acting, but we can use the same analysis. So we can still start with the work-kinetic energy relation. But the difference now is that we're going to include not only the work of conservative forces, but also work done by non-conservative forces. And together, those two are going to combine to cause some change in the kinetic energy. So doing a very similar type of a substitution, we're going to see that we're going to include this extra term, the non-mechanical energy change. And that's something that we didn't see before with conservative forces. And that's going to give us an additional bucket into which energy can be deposited in a system. So if you have a system where friction is acting on the object, not only is the energy going to change buckets between kinetic and potential, but some of the energy can also go into non-mechanical forms, specifically thermal energy. The big idea, though, is that the total energy is always conserved, and that's always true no matter what. So we're just kind of pulling in a non-mechanical form of energy here and saying that if you have friction, well, friction is going to take energy out of mechanical and put it into non-mechanicals. So it modifies our final equation here so that you start with kinetic energy and potential energy on the left, but you're going to end up with kinetic potential in some form of non-mechanical energy at the end, which is typically thermal. Okay, so let's take a look at an example just so that you can be comfortable with how this works. This is an example where we have an object which is going to slide down an inclined plane. It's a 75 kilogram object. It's going to have kinetic friction acting on it, and it's going to have a parallel force acting on it too. And I guess I picked a height and a ramp length here so that what will happen is that the object will end up accelerating down this ramp. So the parallel force in this object is going to be greater than the frictional force. So it's going to accelerate. So the object might start from rest up at the top and then accelerate its way down to the bottom. And a typical question would be, if the block starts at rest, how much kinetic energy does it have at the bottom? So before we actually solve this problem, you have to realize that you cannot just say that the kinetic energy at the bottom is going to be equal to the potential energy at the top. That's not going to be true anymore. In fact, there's going to be less kinetic energy available at the bottom because some of that original energy that was potential is going to be converted into thermal. You're going to warm up the incline and the bottom of the object as this thing goes down, and that's going to take away some of the joules. So we would expect to see a smaller kinetic energy at the base of the ramp because of friction. Okay, so this the top picture is the same, and underneath is kind of our analysis here. So you could say, well, let's start with the work energy theorem. The conservative forces work plus non-conservative forces work is going to be equal to our change in kinetic energy. If you look at the work done by conservative forces, that is gravity, they do positive work. And the positive work is equal to weight times the change in vertical position. So weight times height. That's where mgh comes from. Friction is going to do negative work, okay? And that can be calculated by taking the force of friction times the length of the ramp, which we'll call d. And so you're subtracting this term from the original potential energy. And that's how you're going to find the kinetic energy. Okay, so that's the new physics here. The next line is old physics. We do a substitution to find the force of kinetic friction. Okay, a little bit of review there. Again, d is the length of our ramp. And then you can go ahead and substitute your numbers in. And you end up finding out that weight does 44,100 joules of positive work, and friction does negative 20,000 joules of work as this object slides down the ramp. So your final work that gets done is significantly reduced. The final work that's done is not 44,100 joules, but it's only 23,000 joules, 895. So you've really lost a lot of mechanical energy because friction has been acting. So, the next step for this problem might be then to say, well, what is the actual velocity of, the object at the end of the ramp? And of course, you can just solve for that by setting the 23,000 equal to 1/2 mv squared and solving for v. So my point in showing you this is to show you that, friction is taking away joules and it's leaving you with less kinetic energy at the end. Okay, and the very last thing here just to comment on is that come back to that number, the work that's done by friction. The work done by friction is negative 20,000 joules. And that work that's done by friction is equal to the negative delta NME. Okay? And remember, that's kind of the same thing that, work done by a force is always going to be equal to a negative delta, a negative of a change in something. So I just wanted to show you this because the negatives here cancel, and the change in non-mechanical energy forms is actually an increase of 20,000 joules. So what that means is that you've generated 20,000 joules of thermal energy. So that's how you can interpret that. So that delta NME is positive because you've made those 20,000 joules into thermal energy. Okay, so that's about it. And then you guys can have a look at your problems, and good luck with those. All right, bye-bye.